So before we start the next lecture named Robots and Jobs, there will be like 5 minutes discussion related to the previous presentation. So if you have questions, so raise your hand.
Okay, thank you. My name is Roope Uustalo. A question on pretty much on the last slide. So technology was exogenous almost towards the end, but in the end you sort of hint that that technology is endogenous and there are incentives of creating various technologies. But are those really mainly technological reasons, or are there other reasons why technology or automation would be faster or slower? The creation of new tasks would be faster or slower?
So yeah, I mean, in some sense, what I was doing at the beginning was to be agnostic about where technology was coming from, and just do comparative statics, meaning how, if technology were to change, how would the organization of production change, how factors would change. And then in the data, I was again being agnostic about that and then backing out what's going on with different aspects of technology. But I think endogeneity of technology is particularly important to my way of thinking, and I also, I think, for the issues in general, because if you want to think about 2 dimensions of technological progress, you know, what a lot of the literature on growth and endogenous growth focuses is the change, the aggregate rate of technological change. And there are advantages to endogenizing that, but you know, even though we've made a lot of progress in that respect, I think it's fair to say we don't have great great reasons for why some periods there's faster technological TFP, etc. But what my focus is on is more like about the composition of technology. And I think the endogeneity there is even more powerful. And that's what I was really focusing on in that last slide, which is given a particular type of know-how, how do we use that know-how? Do we use it for more for automation or more for technological, more for technologies that are introducing new tasks and reorganizing production? And in fact, just a sort of a using this as an opportunity for sort of giving an outline of where these different pieces of work that I have done fit into this. You know, so in the what I presented in the first lecture is based on a paper that's coming out in the Journal of Economic Perspectives, but also much more on, or some more, more fundamentally, on a paper published last year in the American Economic Review, where in that framework, the emphasis is very much on the endogeneity of technology, as well as the issues that I've talked about, and in particular about why these sort of race between new tasks and automation in general can keep the labor share constant and wages growing constant, but during some periods it can slow down. So those issues, but I didn't want to get into all of them in great detail because of time constraints. But those are all the background of the work. And then what I'm going to talk about today is based on a different paper. This lecture is based on a different paper, and then what I'm going to talk about in the afternoon is based yet another paper. So it's the combination of these 4 that I'm talking about. And then the different pieces all come together, and at the end I'm going to try to talk a little bit more about how they come together.
Okay, perhaps one more short.
Thank you for the very good presentation. My name is Tuuli Koivu, and I would like to ask, how about globalization in the model?
Okay, that's another great question. There are a number of issues here that are interesting in the context of globalization. and I hesitate a little bit about how much to say. Part of the reason why I hesitate is because some of it is drawing on work that is very much in its infancy, so I'm not sure. And some of it is because I'm actually going to talk about a little bit of it in the last part of the lecture. But let me actually give you one important idea, which I think is rather important. And one is that, actually two ideas. One is that you may worry that some of the things that we're talking about automation are very much caused by globalization, and that we are not doing a good job of distinguishing what is automation and what is globalization. So hopefully I will try to put that one to rest in this lecture, because empirically I'm going to talk about that. And the answer is that industries affected by globalization are very different from those affected by automation in general. So there's actually a nice separation, and I'll talk about that a little bit. The second is, what's the effect of globalization on these overall changes in on automation, and what's the effect of automation on globalization? And I think both of those are very important. So some of the automation trends, and again, I'm talking about this a little bit in the afternoon, in countries like the US, but also places like Finland, Spain, etc., are part of the global trends, because those countries are actually followers in automation. So there's a spread of technology that's very important. But more interestingly, and that's what we are doing research on at the moment, is that even though you might think that developing countries are immune to automation because they're not introducing robots, they're not even introducing computerized control machines or numerical control machines yet, it turns out that that's not true, because automation in the developed countries changes the global product, global supply chain in a way that then has first-order effects on developing countries. And perhaps I can talk a little bit about that in the afternoon also, but thank you for asking that.
Thank you for your questions. Perhaps we can now start with
Okay.
the robots and jobs.
All right, wonderful. Thank you very much. And I should say that in the first lecture, in addition to the excellent questions that you asked, there were a few other things that I wanted to talk about, and I didn't have time to talk about them. So I will try to come back to the extent possible in this lecture and the next lecture. But just to put markers on, I wanted to talk about skills. So thank you for asking that question. So that is sort of covered, but I will talk about that now a little bit. And I wanted to talk about institutions, and in particular the interplay between institutions and technologies, and what types of institutional arrangements facilitate the right response to automation and new tasks. And I will try to come back to that at the very end of the afternoon lecture if I can. So those are the two big areas that I really wanted to talk more about, and I didn't have time. But what I'm going to do now is sort of delve a little bit deeper into what I started talking about in the first lecture. So in particular, in the first lecture, I tried to paint a picture in which we need to rethink the effects of technologies on labor demand. And in particular, the two legs of that were automation and new tasks. And in particular, perhaps automation was the one that led to the more not counterintuitive, but counter-conventional wisdom implications, where it can reduce labor share significantly, it can reduce employment and jobs, even though productivity is increasing. or even though firms are eagerly adopting these technologies. So at this point, I think it would be quite reasonable for all of you to say, fine, perhaps that works in theory, but does it work in practice? So perhaps you can write down a model in which indeed technologies of automation will have such effects, but is that really an important factor? And then the data I presented goes in some way, but it was rather indirect. It wasn't sort of what you would call causal inference, meaning I wasn't showing you that, yes, indeed, there is a shock to technology that then has these effects that I was tracing out in the theory. So this lecture is hopefully meant to add to the evidentiary basis of that set of claims. So in particular, what I'm going to try to do is try to convince you that in fact I can isolate a set of automation technologies, and that I will show you that the effects of these technologies are very, very diametrically opposed to what you would expect on the basis of technologies just good for labor demand and etc., that in fact automation has very different effects on the labor market. So I'm going to be investigating the effects of robots, and in particular industrial robots. So I'll define what robots are, but these are robots used in industrial applications. So a lot of the background and the data for this comes from a wonderful organization called the International Federation of Robotics, which has collected data and has done a lot of studies. And IFR defines an industrial robot as an automatically controlled, reprogrammable, and multi-purpose machine. So in particular, those robot arms that I showed, what was special about them was that they weren't just doing one thing, like nailing a nail into the wall. They were multi-purpose, they were changing their angle, they were changing their activities, and that was reprogrammable. In fact, as I'm going to talk about in this lecture, about 2/3 of the cost of using a robot, if you're thinking of going into this business, goes to what are called robot integrators. Those are people who come and maintain and reprogram and change the applications of your robot. So that reprogrammability is really important, and automatically controlled, of course. So your coffee maker is not a robot. Your elevator is not a robot. Those are not reprogrammable. They're not multi-purpose. There are dedicated advanced machinery that are, some of them are automation machinery also. So for example, there are automated welders. And those are not robots either, according to IFR, although one might have called them robots. The reason is because you can have a robot that does welding and painting at the same time, whereas an automatic welder does just the welding. Okay? So robots have been spreading fast, as I'll show you, and I will explain why they are actually, not this lecture, but next lecture, while they're doing so most rapidly in Germany, Japan, and Korea. US, actually you'll see in a second, is actually a laggard. So here is the data. This is Germany. Germany is one of the countries where robots have been most rapidly expanding, although South Korea has now caught up with it and Japan has now caught up with it. This is the US. So you can see it's sort of a bit of a laggard. So it starts at a lower level in 1993 when we first have data on the stock of robots, and the stock of robots increases more slowly. So I'm going to focus a lot of my talk today, this lecture, to this period, 1993 to 2007. Why 2007? Because I want to stop it before the recession that hit the manufacturing hard. It turns out it doesn't actually matter, and I might show you some results for the longer period also, but let me focus on 2007. During that period, this increases about 1 robot per 1,000 workers in the sectors that you're relevant, but it's 1,000 per 1,000, one robot per 1,000. In the same time, Germany has an increase of about 3 robots per 1,000 workers, and overall Western Europe has 1.7. So as you can see, US is actually a laggard, and we'll talk about why that is this afternoon. If you look at the US pattern, US is very similar to these countries: Denmark, Finland, France, Italy, and Sweden. So here I'm showing you the average, and Finland is actually ahead of the US, so you'll be proud in robots. And we'll talk about that also this afternoon. So for now, I'm going to take that as a fact, and these are the facts that I'm going to work with. Okay? So where are robots spreading? I'll show you a lot more on this, but robots are spreading, and this goes back to the question that was asked about globalization, especially in what you would call heavy industry. So 39% of the robot stock in the world at the moment is in automotive sector. Electronics, 19%, plastics and chemicals, 9%, metal, fabricated metals in particular, 9%. So if you go to some factories that make car parts, weapons, guided missiles, electronic parts, you'll see complete robotization in many countries, but not everywhere. So many argue that they have transformed work, or they will do so. Many popular books have been written, coming soon everywhere. The future has a lot of robots and few jobs for humans. But, to what extent is that true? And as I've already indicated in the first lecture, these claims all need to be taken with some grain of salt and doubt, not just because their evidentiary basis is weak, but because they're also maybe misinterpreting what's going on from a conceptual point of view. But certainly the claims are there. What do we know about the effects of robots? Well, actually, not a trivial amount has been written on this, and some of them have attracted a lot of media attention. So the Economist article or other publications like that often talk about studies such as Frey and Osborne or several other studies, and McKinsey every month puts out a report on this. The problem is that these reports are based on two legs that are both problematic. The first leg is that they are about projections into the future about what robots or AI or other technologies will do, and not only because of the general uncertainty about the future of technology, but really about the nature of the tasks and occupations. These are based on rather shaky grounds. So, for instance, the Osborne and Frey and Osborne paper, which attracted a lot of attention and is not really very solid in terms of its empirical analysis, assumes somehow that an occupation is going to be automated if there are some aspects of that occupation that they project on the basis of some evidence that in the future can be performed by artificial intelligence or robots. But as also pointed out by this paper, for example, by Arns, Gregory, and Zieren, that evidence really says some of the tasks in that occupation can be automated. So it's very hard to know what will happen to the rest of the tasks. So these sorts of what you might call feasibility studies of automation are rather difficult, and they make lots of assumptions that are very non-transparent. But conceptually, from an economic point of view, even more problematic is that what we care is, what we need and what we care about are estimates of the equilibrium impact of robots. And the equilibrium impact of robots is very different for the reasons that I have already started talking about. First, and most importantly, once you automate some tasks, because of the productivity effect, that creates increased demand for labor both in the sector, because it has non-automated tasks that will expand, and also in other sectors that are producing complementary goods or they're producing non-tradables supporting it. So the equilibrium impact is completely different from what you might be able to get from the feasibility effects. And secondly, less importantly, but not trivially, the fact that something can be automated doesn't mean that it will be automated. That depends on equilibrium prices. So for example, Amazon at some point, quote unquote, automated the whole of its warehousing, but then it's quickly realized that that was very expensive. So then they now use the Kivu robots for only about a third of the tasks in their warehouses. The rest are still done by humans. So the fact that it's feasible to automate doesn't mean that it's actually profitable to do the automation. So all of these requires a different empirical strategy to understand what is it that industrial robots are doing to labor share, wages, employment, and so on. So what I'm going to do is I'm going to first go quickly through a model that's very similar to what I presented in the first lecture, with the difference that I'm going to do this in a context in which there are multiple local labor markets, and this will become clear why I'm doing it that way. And I will show that in this framework, one could write, or one could derive, a pair of equations from the theory that are sufficient for understanding the equilibrium impact of robots. And in particular, those equations shown in blue take this form, that employment change and wage change in a labor market, which I'm going to denote by C, because in the US context, I'm going to approximate them by commuting zones. So essentially local labor market, and I'll explain what commuting zones are. And it's going to be a function of an object I'm going to call exposure of robots. And an exposure of robots in a local labor market is a Bartik-like measure with baseline industry shares in that commuting zone and the technological advances, which I'm going to call robot penetration of that industry. So that I'll show you that this Bartik-like equation is actually the theoretically well-grounded, but it also has the advantage that even if you didn't believe the theory, but you should, this is a sort of a simple Bartik-like measure which we sort of understand what it does in an empirical context. Okay. So, but crucially, this beta E and beta W are themselves functions of the parameters of the model. And then in particular, they might depend on the trade and other interaction patterns across local labor markets, and I will clarify that. So in particular, this exposure to robots is going to use this variation here. So I'm going to trace out what's going on in Denmark, Finland, France, Italy, and Sweden. Again, Finland is playing a very important role here, as a proxy for what US is following. Because if you see, the US is following these countries on average, with about a 5-year delay or so. One could also use Germany, and the results are very similar when you use Germany. But Germany is so far ahead of every other country here that actually it's this is a better measure of where US is going than Germany, because given the big difference between Germany. But it doesn't really matter, but that's what I'm going to do. So this is a similar strategy, although a little bit more theoretically grounded, to the usual Bartik strategies. For example, in the outer Daron and Hansson's work, which I will relate to in the context of globalization, they estimate the effects of trade with China, and then they do a Bartik measure where the driver is what's going on to imports from China in other developed economies. So here we're also using other developed economies, but those that proxy the technological frontier as relevant for the US. And again, the puzzle here at the back of your mind might be, but isn't the US the technological leader of the world? Well, yes in software, yes in biotech, yes in nanotech, yes in some parts of hardware, but certainly not in robots. Why not? That's interesting. We'll talk about that this afternoon. Okay. Now, oops, this is the wrong one. I should put it here so that I don't get confused with this. So, crucially, there are potential endogeneity issues which I will discuss when using a strategy like this. one advantage of using technological frontier is that we are abstracting from trends that are idiosyncratic to the US. So for example, the automotive industry, which I've emphasized, is super important whenever you talk of robots. And the automotive industry in the US has gone through ups and downs. So if you use US data, those ups and downs will be part of your variation. So this sort of strategy will enable us to isolate from that. But anything that's got to do with the baseline industry shares, you have to worry about, and we'll worry about that quite a bit. And just to give you a preview of where we are going, what we're going to find is that, consistent with the theory that I presented in the first lecture, combined with productivity effects not being huge, we're going to find very robust negative effects on both employment and wages. So, in fact, consistent with the task-based framework of automation, and very different from what you expect on the basis of just technological change always and everywhere being a boat that lifts, the tide that lifts all boats, we're going to see that there are fairly distinct negative effects. Moreover, these will increase inequality. They will hurt middle and low skilled workers particularly, and then we'll see how they affect the occupational and industry structure also. So this is related to all of the literatures that I hinted at in the first lecture, but now that I have a little bit more time, in particular on the wage inequality literature that that I've already sort of mentioned. So in particular, work by David Otter and colleagues and several other people have looked at the employment polarization. So we'll see the effects of robots very clearly, but differently from many of the other works here. We can sort of hopefully get to a little bit more the causal effect of a specific class of technologies. So the only other paper that, well, there are now a couple more, but the first paper that investigates the effects of robots is the important work by Georg Graetz and Guy Michaels. But the difference here is that they look at the cross-industry, cross-country variation, whereas what you'll see here is that we're going to be able to focus on the technology frontier-induced effects on local labor markets. And then I'll talk about this interesting paper by Greenlee and Kraft as I go along. Okay, so theory. Theory is very similar to what we talked about, but let me be just specific about a few things because I'm going to build up to the estimating equations from the theory. So let me first shut off trade between commuting zones. Obviously, New York trades with Alabama, and all of those are very important, both for actual data and conceptual interpretation. But let me start without trade for a second, and I'll come back to trade. So local labor markets are indexed by C. They're going to be these commuting zones, 722 of them. So in the US, you have these choices about what local labor markets are. One could use states, but states are very big. So Texas is a huge state, so one might then use counties. Counties, there are many, many of them, but they're very integrated. So it's not very reasonable to use counties as local labor markets. One could use cities, but that then leaves out all of the areas outside of the cities that many of them feed into the cities. So one thing that the census economists developed about 20 years ago or 15 years ago is these commuting zones, which is look at the commuting patterns and trace out county groupings and county borders, sometimes dividing counties into halves, of where people commute to, and then out of those you create local labor markets. So that's what I'm going to focus on. Why So why CI is the output of industry I in commuting zone C. And then we're going to assume that output in commuting zone C without trade is just a YCI, but with these weights omega I, or sorry, nu I, that determines how important each industry is. And again, I'm taking the elasticity of substitution now between these industries to be sigma. Okay? So the key is about how different different tasks are produced within industries. And there I'm going to assume that XCI, which is the production of industry I in commuting zone C, is equal to some constant. This is important, ACI. So that's the productivity of industry I in county C. And then you combine that with capital and these tasks. And here I have simplified things. It doesn't really matter, but rather than have that integral of tasks, I just took a Leontief technology. So between 0, 1, all of the tasks have to be performed. So it's the minimum of all of the output of the tasks. But the key thing here that I would like to draw your attention to is this ACI. So ACI is going to be the thing that determines why you choose to produce cars in Detroit but not in Wyoming. So local knowledge or local productivity of cars is higher in one area versus another. So that difference is going to be the reason why different commuting zones are going to specialize in different industries. And you'll see as I go along that there's a huge degree of persistence in that specialization. So if you look at the current industry distribution of employment in the US, it looks not that different from what it was in the 1960s, 70s, 80s. Each task then is produced in the same way as before. Those tasks that are about theta I can only be produced by labor. Those tasks below theta I are automated. They can be produced by labor or by machines. MCI is the machine. So crucially, and that's why I'm going through this, theta I, what I used to call I in the previous part of the lecture, is now industry specific, and that's why I'm calling it theta rather than I subscript I, because that would be a little bit awkward. So theta I is going to be different across different industries. So here one robot, if you have an automated task, replaces gamma L over gamma M, or gamma M over gamma L workers. Let RMC denote the price of robots, WC the wage of workers, then the cost savings from robots, that's where the productivity gains that I talked about, are equal to pi c, 1 minus RC over gamma times WC, where gamma is this ratio. So this is reiterating what I said in the previous lecture, which is that the higher is the wage and the lower is the R and the higher is gamma, the more productivity gains you're going to have. But this is, of course, going to vary in general. I'm going to assume that there's a supply of labor, some elasticities here. I'll come back to this, that's important. So epsilon is the Frisch elasticity of labor supply, or the inverse of the Frisch elasticity of labor supply. So I'll come back to that in a second. And then, this is important, I'm going to assume that the supply of robots, machines, to a commuting zone is upward sloping, and the elasticity of that is eta. Why should the supply of robots to an area be upward sloping? Well, the reason are these integrators. So as I've mentioned, about 2/3 of the cost of robots comes from these integrators, and the integrators are always local. They need to be local because the use of robots involves constant work with the integrator. So even companies that are extremely robotized, like General Motors and Raytheon, that use millions of dollars of robots stock in each one of their factories, make heavy use of integrator services. Because the actual programming and maintenance of these machines is very specialized. And so that's the reason why to the local economy, potential cost of robots would be increasing when you want to use more robots. Okay. And then you have a bunch of market clearing conditions. So these eta and epsilon are going to be important parameters when we come to interpret the model in a second. All right, what's the effects of robots? Well, it's exactly what we saw before, but let me highlight it just again, that when I change, suppose pi c is positive, meaning that you will adopt the robots, then the change in demand is given by a productivity effect. Because of the robots, we change productivity, and then the price of the good changes. So this is a composition effect, and it depends on whether you expand or contract your production, or how much you expand your production, when your prices change. So in particular, when I introduce a robot into a particular sector, and I reduce costs, why do I reduce costs? That's the productivity effect, pi c is positive. That sector's prices are going to fall, and that sector is going to expand. If that expansion is very strong, in fact, that sector's own demand might increase. So that's the composition effect. But always there is a direct displacement effect, which is what I've emphasized, and that's always there. So if the productivity effect is small and this composition effect is small, employment will necessarily fall in the industry. Now aggregate this up from the industry to the whole local economy, and you have these equations linking wage and employment in the industry to what's going on. And what you will see is that both of these equations on the right-hand side have the same term. So this delta theta I 1 minus theta I term, which was the displacement effect at the industry level, you multiply that by LCI, which is the baseline employment share of that industry in the local economy, in the commuting zone. So you see that everything depends on this Bartik-like measure in theory. So that's why we're going to be using that Bartik-like measure. What is the coefficient here? Well, now we can see the coefficient has a displacement effect, exactly like what I showed you before, the productivity effect, and then it also has an income effect, which is, the composition effects across industries cancels out. You win, I lose. That's going to cancel out. But there's an income effect, which is the residual of that composition effect, because we are sort of getting richer, and that's well, it's not getting richer. It's effect on labor supply. The getting richer is in the productivity effect. So there's no composition effect on aggregate because all of these things are canceling out. So this is this. So, but what's unrealistic here? Oh, the other thing I was going to say, this displacement effect and the productivity effect, you see, they're going to depend on this eta parameter that I highlighted, and the income effect is going to depend on the Frisch elasticity, the epsilon. Okay. But of course, what's unrealistic about this is that Detroit introduces robots in the car manufacturing sector, and that has no effects on Illinois. Of course, that doesn't make sense. If cars become cheaper in Detroit, Detroit's going to export all of these cars to the rest of the United States. So it's going to create both income and productivity effects for the rest of the United States and various more complicated composition effects. So to do that, let's generalize the framework and assume now that we can trade between different commuting zones. But I also don't want this to be a completely open economy with no frictions, because that doesn't make any sense either, because a lot of the things that are done in a local economy are for consumption in the local economy. So the way that we do this is then introduce a non-tradable good non-tradable services, as well as a tradable good. Tradable good is traded, non-tradable good is not traded. Phi is the share of the tradable good. And then assume that the tradable good is done in an Armington-Anderson way, where you source inputs from your tradable good from different commuting zones. So YCI uses services sourced from other commuting zones, which is denoted by S in this instance. So each one of this XCI in turn is then produced in the way that I explained, either with robots or with labor, depending on what degree of automation there is in that industry. Okay. So now we have exactly the same framework as I just went through here, but with two additions. One is that automation in one industry is going to affect another. Automation in one commuting zone will affect other commuting zones. Now through two channels potentially. One is because it's going to change prices, and second because some of the capital stock in that industry might be held by people in another commuting zone. So capital gains or capital income is not necessarily in the local economy. So those are all allowed here. And then the second issue is that there are these non-tradable goods. Okay. So if you go through the math, it turns out that it again takes exactly the same form. So in particular, we can write the overall impact on employment and wages in a local economy as a function of exposure to robots, where exposure to robots is this term here. Or more explicitly, now let me do this. I'm going to write exposure to robots as the sum over baseline employment shares of something I'm going to call APR, which is adjusted penetration of robots. And the adjusted penetration of robots is how much does the stock of robots changes by relative to baseline employment minus output change times MI over LI. This second adjustment factor is necessary because there's an expansion path of robots and you want to need to take care of that, and that's exactly equal to this term here. So if you ignore this term, this doesn't really matter because it's small, but then this would be approximately the equality, but according to theory you should have this second term. Whether you do or not in practice, it doesn't matter. So the crucial thing is, therefore, is that both in the model without trade and in the model with trade, the same equation can be used for understanding the effects of robots on local employment. However, crucially, and I'll come back and spend about 5-10 minutes on this at the very end when we come to interpreting magnitudes, these coefficients in front are different depending on whether there is trade or not. And the reason for that is very simple. If this was a world of autarky and I want to compute the aggregate effects of robots, I just compute the effects of robots commuting zone by commuting zone, and I sum over these 722 commuting zones and I get the aggregate effects. But in a world with trade, I cannot do that because there are spillovers between these commuting zones. So I need to take those into account. Okay. All right, that's all the theory. So now with this theory, we can go to the data. And I've essentially told you what we're going to do in the data. We're going to compute this exposure to robots term, in particular using the technological frontier coming from the more advanced economies, such as Finland, and then estimate these equations and interpret them, and then worry about causality and various things. So data sources, I've already told you the key thing coming from the IFR, but we're going to use a lot of other data sources, including census, American Community Survey, county business patterns, IRS data, and various other data sources. But the key is these IFR data. It starts in 1993 and it's available for 19 industries. Some of them are very aggregated, but it doesn't matter because they are the industries that are not adopting much robots, like education, health, etc., being bunched together. And then there's some detail in the industry front. So in particular, the key object is this adjusted penetration of robots that I've already indicated. And US exposure to robots is this, but I'm going to focus in a lot of this is this exposure to robots that comes from the APR bar, which is the one that comes from Finland, France, Denmark, Sweden, and Netherlands. We're going to use baseline employment shares. As I said, they are very persistent, and there's already some rapid automation going on in the 1980s, so I'm going to use the 1970 baseline shares, but it doesn't matter too much. So let me show you some data now. This is where robots are being adopted in terms of industries, and the circle size is the size of the industry, and the horizontal axis is our measure coming from Europe, the frontier, and the vertical axis is the US. For US data, actually, is very low quality, cannot be industry decomposed before 2004, so I'm showing you 2004, 2007. So you see services is the hugest sector because it's an aggregate here, and it's not adopting many robots, very small. Automotive industry is the leader in both. The US, you see it's the highest adoption. But the thing that's important here is that leaving out miscellaneous and shipbuilding and aerospace, which is the one sector in which US is more robotized than these other countries, not as robotized as Germany, but they're very, very closely correlated. They're all pretty much around the single 45-degree line. So one set of concerns in interpreting any regression about the effects of robots is that you may be worried that robots are introduced in other places, in industries, where other technological or other major trends are having a first-order impact. And the globalization point that was raised was about that. So in this graph, although now I think now we've replaced this graph in the paper with a correlation table, but I think for a talk table is hard, so I'm still sticking with this graph, although I'm less keen on this graph than I was before. But anyway, if you look at this graph, you will see that there isn't much of an overlap between robots and other changes. So in particular, these are the industries: automation, metals, plastics, and then metal products, and so on. And the first one here, brown, is the robots. So those are the industries that are introducing robots. And then the next ones show you other trends. For example, the blue is the imports from China. The yellow is IT capital. There's offshoring. There is overall change in capital stock. And you will see that the correlation between any of these measures and robots is extremely weak. So, in fact, the relevant correlation, which you cannot see here, and that's why a table, in the final published version of the paper, it will be a table, is the relevant correlation is when you condition on manufacturing. because you don't want to compare manufacturing versus non-manufacturing. So when you condition on manufacturing, the correlation between imports from China and robots is negative. The correlation with IT capital is 0. The correlation with overall capital stock is 0, etc., etc. But even unconditionally, most of those are pretty close to 0. So robots are affecting a very different set of industries. So this doesn't mean that they are exogenously assigned, obviously, but they're not capturing some other trends, and I'll come back to this issue later. So one thing based on theory that I highlighted, I didn't repeat here, but I highlighted in the first lecture, is that if something is an automation, it should reduce the labor share. So if you call some technology an automation and then you show me that as it was being introduced, labor share was increasing, that's, at least according to this conceptual framework, wouldn't make much sense. In fact, that's exactly what happens at the industry level. If you look at industries where this adjusted penetration of robots, again, I'm using the frontier, is going on, you have large declines in the labor share. The automotive industry, plastics and metals, plastics and chemicals, metals, etc. So these are the industries that are driving the decline in the labor share. And this is also a concern that you might be worried about, is that some of those might be declining industries. So you may be worried about the automotive industry, for example, being in decline in the US. We hear about that a lot. But actually, the robotizing industries are not just increasing their value added per labor, they're actually increasing overall value added faster than other industries. So in fact, the automotive industry during this period of robot expansion is increasing its productivity hugely. So robots are associated with greater productivity. Now that's interesting because I've also got some other work I'm not talking about here, but if you look at overall IT capital, you don't see this. So computers haven't increased productivity in manufacturing. It's a very interesting thing. But robots, you see the increase in productivity. And also at the industry level, you see that you get a decline in employment in industries that are adopting robots. And here I'm showing you this in two sub-periods. The red is 2000s, the yellow is the 1990s, and you see in both sub-periods you have a decline in industries that are adopting more robots. So, summary, consistent with what I talked about in the first lecture and consistent with what I'm proposing in terms of a conceptual framework, in places where the US is adopting robots, because the technology frontier is moving ahead and following the technology frontier, you see large declines in labor share, increases in value added, large increases in value added per labor, and declines in labor. So overall, manufacturing is becoming less labor intensive. But what are the equilibrium effects on local labor markets? So I turn to that next. So this is the map of the US with dark colors showing more intense exposure to robots. You see where robots are being adopted. It's a lot of it is in this industrial heartlands. As I pointed out, the unconditional correlation with China shock is 0.05. Unconditional correlation with share of routine tasks is 0.3, because all of those happen here and here. Those are much more on the coasts, especially the lower coasts in the US, because that's where things like toys, textiles, computer assembly, sort of lower value added, lower tech things. And then as soon as you put the manufacturing share, that declines to 0. So this picture is very different from what you would get on the basis of globalization, etc. Now, one thing that you would definitely want to know is that, in fact, this exposure to robots measure that's following the frontier actually predicts adoption of robots in the local labor market. So in other words, remember what my exposure to robots measure is doing. It's looking at your baseline industry structure and saying, oh, you have a lot of plastics and electronics and cars, and the frontier for robots is moving fast, therefore your exposure to it is high. But what I would want to show next is that you're also adopting a lot of robots locally. Unfortunately, at the moment we don't have firm level robots data. We're actually collecting those with the Census Bureau with a new census survey, but that won't be available for another several years. So we can't do that. But this is where this interesting paper by Lee Green and Kraft comes in. So they are these two, Lee Green is a professor in the Georgia Tech, and Kraft was a PhD student of hers in operations research. So they scraped the web to get the location of all robot integrators in the US. So even though we don't have local robots information, we know where the local robot integrators are. And as I said, if you're going to adopt robots, you need to have local integrators. You can do a little bit by having people flown in from other places, but if there's a lot of robots activity in the local economy, you need to have robot integrators. It turns out that that's very strongly correlated with our exposure measure. So let me show that in a figure rather than in the table, and then the table has exactly the same format as the other tables, but I don't want to introduce that format yet, so as to economize on time. And so on the horizontal axis, I have the exposure to robots, again, the one driven by technology frontier. And here I have log of robot integrators in the local economy, 1 plus log. You can do other things like Poisson models. It doesn't change anything. And these are the different commuting zones. The circle size explains the commuting zone, is proportional to the commuting zone. And you see the variation coming in. There's quite a bit of variation here, and then there's a bunch of commuting zones which I've labeled, which are the ones where a lot of the specialization in industries where robots are being adopted are. So Detroit, Lansing City, Michigan, Saginaw City, Michigan, Lorain City, Ohio, Wilmington, Defiance, Ohio, Delaware, and Wilmington, Delaware. Sorry, Wilmington is Delaware. Sorry, and a couple of others. So the solid line shows this relationship, which is fairly precise, and it's this one here. I will explain to you what the covariates are in a second, but this is the sort of the baseline specifications that we have. So this is this is what I was saying. It's a fairly precise relationship with a t-statistic of about 5. But you may be worried that this relationship here is being driven by this very high places like Detroit. So the dotted line then leaves out all of these high exposure to robots, the highest exposure to robots places. So it's just estimated from this cloud of points. And then you see that it's a little bit steeper and a little bit less precise, but it's the same. So in terms of the regression, this is this. So it's, oh, sorry. It's this, it is this. So it's the t-statistic goes down, the coefficient goes up, standard errors goes up, but the relationship remains fairly similar. And what are the covariates here? Well, I would say this controls for all of the covariates that you want to control for, but what they are, I'm going to tell you in 1 second. Because I'm going to tell you in 1 second, because what I want to do now is jump to the main specifications that we care about. Those are the ones that are about employment and wages, as we emphasize in the context of the theory. So let me focus on employment first, for no reason other than I think people emphasize employment more. That's why the paper is called Robots and Jobs. But to me, I think the wage implications are as important. So here is the first column. This, and let me, I have hourly wages here too. At some point I had them in separate tables. Now I'm using this one. Okay. So this first column, and again, let me focus on the panel A, is looking at the effect of this exposure to robots measure on change in employment to population ratio 1990 to 2007. Population is in the denominator because there may be some effects on migration. We'll come back to that in a second. It turns out it's very small, but it's better to look at relative to population. And here, there are no covariates. The only thing are the census division dummies so that you're not controlling the south to the north. Okay? So you have a fairly negative and precise correlation between this exposure to robots measure and change in employment. This is, if you want to think about it, is like the reduced form of the IV, because I'm still looking at the European measure here. I'm looking at what the frontier is doing. So I'm not sort of IVing what's going on in the economy. Now in the second column, I add demographic controls. So different commuting zones are very different in terms of their skill composition, age composition. So this adds very detailed demographic controls. So share of different age bins by 5-year age bins, different races, different education groups by 5 education groups. So very flexibly allows commuting zones on different demographic compositions to have different employment trends. It doesn't change anything. The third column adds broad industry shares. So different subgroups of manufacturing, you can also add mining, construction, etc. It doesn't really matter. But that doesn't change much. The only one that matters a lot is manufacturing, but it doesn't change this coefficient. And then here, we add imports from China, because again, there's a concern whether they're affecting the same industries. I showed you it's not, but still. And the share of routine tasks, because perhaps it's not robots, but some other technological progress that's automating routine tasks. That would be interesting in and of itself, but it wouldn't be robots, so we do that. But as I said, again, those are fairly orthogonal, and unsurprisingly, you see the coefficient just barely changes. So, pictorially, this is how it looks like. You see now the cloud of points here, and these are the most exposed places, again, Detroit, Lansing, Saginaw, etc. Now you see that even much more than the robot integrators, which was a much noisier measure, this is a really precise relationship. The higher is your exposure, the lower is your employment. And the dotted line is this specification here. When we exclude those guys, you see it's not very different and very precise and similar, regardless of whether you have places like Detroit, etc. So on the basis of this, there's a striking and very robust relationship that commuting zones that are more exposed to greater robot penetration are on a significant downward trend in terms of their employment. Same thing for wages. For wages, we do this composition adjusted since there's an effect on employment, and I'll show you later that that effect is more on some groups of workers. So, so these are composition adjusted at the cell level, but let me not get into the details too much. It doesn't really matter. But you see that the effects are, again, very stable across specifications and very negative. And here it is, the visual representation. Again, regardless of whether you drop these high exposure places or not, very similar relationship, and this cloud of points is very tightly clustered around this line. So these commuting zones that are also the places where there should be the most impact of robots are really doing, not so well in terms of their employment and wages. Now, these are long difference specifications, which means that I'm looking at the change from 1990 to 2007. But if you look at the data, you will see that different industries adopt robots at different points in time. So for example, the automotive industry in the US and in countries like Finland, etc., has a burst of robot adoption in the 2000s, whereas aerospace and shipbuilding starts adopting faster in the 1990s. So therefore, the effects of robots should happen at different points in time. So to investigate that, we do this now in a stacked differences for two periods, 1990s and 2000s, and then we stack them together. And those are the specifications that I'm now showing you. And and these are the equivalents of what I showed you, and things are now more precise because we have more variation. But the one that I would like to draw your attention is these ones. When you have two observations per commuting zone, that now enables you to allow for commuting zone linear trends. And that's a potentially very demanding specification because it only exploits within commuting zone differences. So it only exploits the fact that your commuting zone is more focused on shipbuilding, so therefore the effects for you should be larger in 1990 than 2000, and for me it should be larger in 2000 than 1990, and it takes out everything else, and it just does within commuting zone comparison. And it turns out that the estimate is very, very similar to the baseline that you get. So this really happens exactly with the right timing relative to the adoption of robots. But still, that doesn't tell you about whether this is legit to be interpreted as a causal effect, because it might still well be that even with these linear time trends, there is something different, linear commuting zone trends, there is something different about these commuting zones before the robots were adopted. And here we can do something to alleviate those concerns, because there is essentially not much robotics going on before 1990. So what we do in this table is to look at the pre-trends of the same commuting zones before the robots came online. But since time is short, let me just show you the figure rather than the table. And here are the pre-trends for employment and wages. So there's absolutely no relationship between the exposure to robots and what was happening before. And the same is true for a series of other labor market variables, which I'm not going to show you, but we look at about 10 different labor market variables, and none of them show any trends before 1990. Okay. Now, one other thing that you might worry about is that because automotive industry plays such an important role in robots, that everything is being driven by the robots, automotive industry. So what this table does is that it separates the exposure to robots into two orthogonal components: exposure to robots in automotives and exposure to robots in other industries, and enters both of them at the same time. And the nice result here is that they have very, very similar coefficients. So the automotive industry is not special, it's not driving the results. And in fact, if you leave automotives, you get exactly the same coefficient, because what seems to matter is the stock of robots in general. That might first appear a little strange, because you might think robots are very different in different industries. But actually that turns out to be not true. That there are about 5 types of robots, and they are very similar in terms of their costs, and they're very broadly distributed across industry. So the robots that you use in automotive are not that different from the robots that you use in electronics, metalworks, or shipbuilding, for example. Now, the other thing which I already hinted at is that robots are very different from other technologies. But you might still worry that our changes are being confounded by other technologies, or you might worry that actually other technologies are perhaps having effects similar to robots. But that shouldn't be the case, because as I've highlighted, overall capital deepening in the framework that I presented in the first lecture is very different from automation. And IT capital, computers have an automation component, but they have a lot of complementary features, and they introduce new tasks, they do a variety of other things. So IT capital should be very different also. So this is what we do in this table. And for brevity, let me just focus on one specification, our baseline specification with the full controls. And this is capital and this is IT capital. First of all, you see that these coefficients for, oh, sorry, these are the wages. Wages, sorry, and employment are very similar to what we had. But more importantly, look at these coefficients. More capital increases employment, increases wages, and has a slight positive effect on employment. More IT, same thing. No effects on employment, but higher effect, positive effects on wages. So robots are very different, because robots are capturing automation, and automation is very different from just overall capital deepening. Now, putting all of these together into IV estimates, that's going to be not that hard, and you do that, and the coefficient's actually going to be not that different, because the first stage has a coefficient close to 1. Because, you know, European countries, as I said, are adopting 1.7 robots. Americans are adopting just over 1 robot, so it's not that different. But the more interesting thing is the quantitative implications. So, so let me spend 5 minutes on quantitative implications, and then I will just show in 1 minute some heterogeneity results, and then I will conclude. So let's first think of quantitative implications at the local level. Meaning, this is the thought experiment. Your commuting zone is introducing a robot, and another commuting zone is not introducing a robot. What happens to your wages and to your employment relative to that commuting zone? That's a very easy computation, because our coefficients give you exactly that. All I need to do is turn those coefficient estimates that were minus 0.5, etc., into numbers that you can interpret. And that's what this does. It says that 1 more robot per 1,000 workers, which is essentially the US average, if that happened in a commuting zone, that commuting zone relative to another one which introduces no robots would have 0.37 percentage points lower employment and about 0.75% lower wage growth. So these are large but not huge numbers. So in particular, if this number applied everywhere, it would imply that 1 robot is displacing about 5 workers. And that's more or less what the engineering studies show, that robots on average do the work of about 5 to 6 workers. So the puzzle would be that with the productivity effect, you would have expected that a little bit lower, but you know, that's, if the productivity effect is not huge, that's what you would get. And the effects on wages is fine too. So these numbers are large, but they're not huge. So for example, again, if you project these numbers into the US economy, it would say that the 120,000 robots would lead to about 750,000 less jobs. So that's less than 1% of the US employment. So not huge numbers. So certainly these numbers would not support anything that says robots are bringing the end of work, but there's significant effect on jobs. But this computation here is not correct for the aggregate. It's correct for the local economy, but it's not correct for the aggregate because of the spillovers. So when you adopt robots, that's going to create positive effects on me. So I need to take those into account. How do you estimate those? Well, those are hard to estimate through regression. So what we do is that we then take parameter values that have been estimated or accepted elsewhere. And then under those parameter values, we can then calibrate what the effects at the aggregate would be. And the key parameter values really turn out these this cost saving and the Frisch elasticity. But in any case, it turns out that the results are not super sensitive to the parameter values. But let me just give you the bottom line, that if you do those things, there are major offset effects, but qualitatively things are similar. So the aggregate effects are, instead of 0.37, is 0.2. So instead of 750,000 jobs, it's 400,000 jobs. And instead of, for the wages, the effects are larger, or the offset is larger because of the income effects, because robots create an income effect for the aggregate economy, not the local economy. So that's why the effects are a little bit larger. So the wage effects are halved from about 0.75 to 0.3%, 37%. Now, one implication of this is that a lot of these large effects are coming from non-tradables. That the local economy is going down partly because of the non-tradables. And so one interesting set of questions is, do we really see the effects of robots where we expect them? And do they really spill over to non-tradables? So to do that, what I'm going to do next in the remaining 2 minutes is look at heterogeneous effects. And the answer, just summarizing, is yes and yes. You find the effects where you expect them, but plus spillovers. So here is, the next two are the most interesting in this respect, but then I will show you a few other things. First, this is manufacturing. So you see the effects, actually, again, the final version of the paper, which we are just finished, we realize this is not nice because we're showing the unweighted estimates here, and the unweighted are always a little larger, so that makes it a little bit harder. But just focus on these two. The unweighted is fine, but it's just makes it visually less pleasing. So you see the effects is on manufacturing, the tradable sector, and especially manufacturing in the highly robotized industries. So split manufacturing into industries where robots are spreading and robots are not spreading. So this is textiles, toys, apparel. There's no effect there, and it's all in automotive, electronics, metal products, pharmaceuticals, wood products, which are really heavily automated, shipbuilding. So this is exactly where it should happen. But then look at retail. You see a spillover effect on retail because the local economy goes down for the manufacturing, and then that spills over onto retail. And that's exactly what happens in the model, should happen in the model also. What about occupations? Again, as I've emphasized, automation is about the production workers. It's not the non-production workers. Those guys are still there, up there. They're doing the reprogramming, back office work, planning, and so on and so forth. But that's exactly what you find. Where are the negative effects? Manual operators, operators and assembly workers, blue-collar workers are here, and you don't see much of a positive, negative effects anywhere. Now, we would have expected some positive effects here, managers and managerial supports and professional jobs, but we don't see them. But I think at the end, the reason why you don't see them is because of the non-tradable sector. Non-tradable sector is very intensive in these managerial and professional jobs, and the non-tradable sector is going down, and that's part of the reason. Now, these are the picture as far as the effects of robots on local employment structure, local occupational structure. So you see we've come full circle from the first lecture, where we talked about automation changing the occupational structure, changing the industry structure. That's exactly what you're seeing. These are the middle occupations that are disappearing. But then there's one other thing that I wanted to talk about in the first lecture, which was inequality and the heterogeneous effects. And here it is. So I'm now showing you the employment and the wage effects for different education groups. And you see that the burden falls on high school and college, or some college. These are the line workers, the blue-collar workers that are being replaced. And the negative effects are on those. And again, I would have expected some positive effects and positive employment effects for people with graduate degrees. We don't find that, and my explanation for that is, again, the non-tradable sector. And this is the wage distribution by percentile. And again, you see some slight positive, but essentially zero above the 50th percentile, 60th percentile, and negative effects all the way in the lower. So the automation process is indeed related to skills and to inequality, and we can talk a little bit more about that. So overall, this is an example of an automation technology that's really improving productivity, but at the same time reducing employment and wages, highlighting that the effects of automation are very different on labor demand than presumed just by assuming that technology always lifts all boats. Okay, thank you.
I suppose that you have compared these results to German data. What can you say about those? What is different, institutions or what is it?
So I haven't compared them myself, but since this paper, there is a new paper by, Douth and co-authors, but the rest of the co-authors' names I forget, Douth et al., which apply exactly this methodology in Germany. And they use the IFR data. They do a few things. Some of them are good because there is a little bit more detail in German data. Some of them, it's a little, I'm not sure, but I don't think it matters for their results. So what they find is that exactly the same specification, exactly the same regression. There is negative wage effects, but no negative employment effects in Germany. And why is that? Well, one possibility would be that German factory system is finding ways of employing workers while at the same time, because of training, etc., while at the same time automating. And there is some of that I can see from casual evidence and other things that I've looked at. But actually that doesn't explain their results. And the reason why that doesn't explain their results is because if you, instead of looking at employment, if you look at production worker employment, that also goes down. So therefore, what they're finding is quantitatively the effects are a little smaller, but qualitatively is that they're finding exactly the same effect on production workers, and they're finding the same effects on wages. So where is the difference? The difference is that we're finding that non-tradables contracts in affected areas. They find that non-tradables expand. Now, why would that be? Well, there are two possible explanations. One is that local labor markets are less clearly delineated in Germany. So if to the extent that there are more fluid changes in non-tradables in Germany, that might be one reason. The second reason might be that the social safety net might imply that, what's going on here, which I didn't have, I've hinted at, but I didn't have time to explain in the model, is that what explains is that robots come, you reduce labor supply, that Frisch elasticity is not really a preference. It could be preference or quasi-labor market institutions or whatever. So you move along that, your labor income goes down. But if your labor income goes down, your demand for non-tradables goes down. And then you produce less non-tradables. So if for some reason, because of transfers, because of social insurance, or ability to find other jobs for these workers in Germany, you don't have as much labor income decline in the local economy, then the non-tradables shouldn't be as much affected. And in fact, the non-tradables should then expand, because now you have these workers whose relative wage is higher in non-tradables than in tradables. So that seems to happen much more in Germany than here. So one possibility is that local demand effects are different, but that needs to be investigated.